This is a YouTube preview of a section of a course called ClojureScript for React developers. This is part 3 in a series of 3 preview videos. Add local storage. Our objectives are: we will use the local storage web API to save our data so that it doesn't get erased when the page reloads or the browser closes. We will show you how to save to-do items as a string in local storage. We will realize that we cannot use a counter to allocate IDs to new to-dos anymore. We will remove the counter. Finally, we will get saved to-do items from local storage and convert them back from their string representation to a sorted map. In this video, we will add local storage to our app, which will enable us to save our to-do items. Local storage is a web API that securely stores key-value data across page reloads and browser sessions. Local storage has no expiration time. The keys and values are always strings. Let's demarcate an area in our code for local storage. We will first define a local store key and call it TodoApp. Now, define a function to put our to-dos into local storage. Using interop with JavaScript, call the setItem function on local storage. Pass in the local store key as the first argument, and a stringified representation of the to-do state as the second argument. We want this function to be called whenever our to-do state changes. Now, we already have a way of doing this. Our to-do state watcher is invoked whenever the to-do state is updated. We can call our to-dos arrow local store function there. Now, let's check the local storage in our browser. Check on the Application tab in the Chrome Developer Tools. Click on localhost port 3000 under local storage. Now click on the toggle checkbox for the Do Laundry item on the page. You can see within Developer Tools that the local storage with key To-Do app now contains a string representation of our current to-do state. Now click on the Console tab. When starting our app, we want to update our to-do state from local storage instead of using sample data. First, let's make sure our sample data is not loaded when the app is launched. Before a form, if you use the dispatch character, which is a hash sign, followed by an underscore, this tells the Clojure reader to ignore the form. It is called the discard sequence. Now, the app will not be initialized with the sample data. Now that we are going to rely on local storage to hold our to-dos, we cannot make use of the counter state in our app anymore. Let's delete the counter. When adding a new to-do item, we want to find the highest ID of the to-dos we currently have, and then provide the new to-do item with an ID which is 1 higher. We will add a utility function to allocate that ID. We will call the utility function allocateNextID with the to-dos map as its parameter. We will increment the last key of the sorted to-dos map. However, there is a bug in our code. If the to-dos map happens to be empty, then calling keys on it will result in nil, and calling last on nil also results in nil. Calling inc on nil, however, will result in an execution error. We will need to deal with this case. We will use the fnil function, which takes a function f and returns a function that calls f, replacing a nil first argument to f with the supplied value x. In our case, f is inc, and the supplied value x is 0. Basically, we are replacing nil with 0 for an empty to-dos map. Hence, we will allocate the ID of 1 to the first new to-do. In our addToDo utility function, we will now need to change the ID binding. We will call allocateNextID on the to-do state map. Next, we will define a function which will read the stringified to-do state in local storage, convert it into a map, and update our to-dos atom. We will call the function localStore arrow to-dos. First, we will create some local bindings. We will name our first binding Eden Map To-Dos, which will get the value of our app's key in local storage via JavaScript interop. We need to convert the Eden string into a Clojure map. This requires that we use a function called readString, which we can find in the cljs.reader library. We can now make use of the reader. Create a binding called unsorted to-dos. We will take Eden Map To-Dos and read them using the readString function, first guarding against a nil value using the SumThreadLast macro. In our last binding, we will put the unsorted to-dos into a sorted map. Now, simply reset the to-dos atom with the sorted to-dos. As a final step, we need to call this function when the app is loaded. We will go to our main function. Call it before we render the app. Now, when we reload the browser, the to-do state will be pulled in from local storage before the app renders. Good. We can see that our to-do items are still there. Saving our to-dos to local storage now works. Add routing. Our objectives are: we will use a ClojureScript library called Secretary to implement client-side routing. Please note that we won't go into how routing works in detail, since that is outside the scope of this course. We will make use of several Google Clojure libraries, which will be very helpful for controlling the browser navigation, which includes the back and forward buttons. We will promote the showing atom to the scope of the namespace, where it will be part of our application state. We will show you how to create routes, including those containing parameterized strings. And we will connect the anchor links to these routes. We want to enable routing in our app so that we can see which filtered view of the to-dos list is showing in the URL. We will use a client-side routing library called Secretary, which has been around for many years. There are several popular ClojureScript routing libraries. Secretary is the routing library used in the Reframe documentation for their TodoMVC example. And since we are covering Reframe in the next section of this course, we have chosen to use Secretary here too, to make it easier to compare implementations. We will need to add Secretary as a ClojureScript dependency. To do that, we will open the shadowcljs.eden file in the project folder. Add the secretary dependency after the reagent one. Based on secretary's documentation on GitHub, we will need to add the following package information. Save your changes and return to the source code file. Since our dependencies have changed in shadowcljs.eden, we'll need to restart the development server to download the new dependencies. First, shut down the server with Ctrl-C. Now use the npm start script to start it up again. Wait for the build to complete. We will fast forward in this video to when it has completed. Now that our server is running again, we will reload the browser. With the restart, we have lost our app state. Let's make use of our sample data again. Remove the discard sequence and save the file. Now that the sample data has been reloaded, let's put back the discard sequence. Now let's implement client-side routing for our app. First, we will require secretary in our namespace. From secretary's documentation, we'll also need to refer a macro called defroute, which will help us define our routes. We will be requiring several Google Clojure libraries in our namespace as well. Add goog.events and alias it as gevents. Add goog.history.eventType and alias it as eventType. And we will do an import of goog.history.html5 history. We will now make use of these libraries. Demarcate some space for hash-based routing below utilities. First, we will define a function that will control our browser navigation. It will use the DOM window history object via Google Clojure's HTML5 history class. We will supply an instance of the HTML5 history class to the do_to macro, which first evaluates it. And then calls any following functions with it supplied at the front of the given arguments, in the order given. The first function will be an event listener, which listens to the instantiated HTML5 history class supplied by the do_to macro as its first argument. Its second argument will be the type of event listened for, namely the navigate event type. We will put this argument on the next line. And as the third argument, we will supply an event handler on the next line. The handler will call secretary's dispatch bang function, passing in the event token. We are getting a build warning saying that the target type in the expression involving our event token cannot be inferred. We will add a type hint to our code to get rid of this warning. We will pass a second function to the do_to macro, which will simply call setEnabled on the HTML5 history instance, setting it to true. Before we declare our app routes, we will need to move the showing atom out of our to-do app to the global scope of the namespace. Remove the showing argument from the task list and footer controls. We will also need to remove the showing parameter from both the task list and footer controls component definitions. Now, we will need to define showing as a ratum in the global scope. We will now define a utility function for resetting the showing atom to a particular keyword value. We can start defining the routes. Since we will be doing hash-based routing, set the configuration in Secretary to prefix routes with a hash character. We will first describe Secretary's defRoute macro. It defines a link between a route matcher and an action. The string argument following defRoute shows the route to be matched. The argument after that contains any parameters extracted by the route. The third and final argument is the route action, which we will use to set our showing keyword. When we are on the base route, show all the to-do items. Our next route matches against a base route followed by a parameterized string, which we will call filter. The filter string, which in our case is one of the strings all, active, or done, will be destructured in our next argument. The destructured filter string can then be used in the final argument, the route action, where it will be input as a keyword in the setShowing utility function. Now that our routes are defined, we just need to call the hook browser navigation bang function at the end. Now let's set the target hyperlink references of our anchor links labeled all, active, and completed. Remove the hash string to start. We will create a new string consisting of the hash for hash-based routing followed by a slash. And at the end of the concatenated string, put the name string of the filter keyword, that is, the part without the colon. Finally, we will call the appRoutes function just before we render the app in the main function. Let's see if it works in the browser. Let's mark the first item as done. Click on Active. The browser address bar shows #/active at the end of our URL, which is what we want. Click on Completed. The browser address bar looks correct. Now let's try the browser back button. Good, it works. We now have routing in our To-Do app. Refactor to use reducers. We have a single objective. We will refactor two of our utility functions to use reduce, in order to prepare our code for adding reframe in the next section. Arguably, our code will be easier to reason about. We will now start with the rewrite of our utility functions. First, we will refactor the clearCompleted function. To start, let's comment it out. Now, let's start a new version of it. First, we will find the IDs that are done and put them in a sequence. To do so, we will start a thread_last macro on the values of the to-dos map. We will filter on those for which the done field is true. Finally, we will map over them calling their ID. This results in a sequence of ID values representing the to-do items that are completed. Next, define a binding named updated to-dos. We will make use of the reduce function. Reduce's first argument is a function of arity 2, optionally followed by an argument representing the initial value of the accumulator, followed by an argument for the collection which is operated on. As the first argument, we will provide the dissociate function, which takes a map and a sequence of keys as arguments, returning a new map with the keys and their corresponding values removed. As the second argument, we will supply the initial accumulator value, which is the value of our to-dos map. The final argument will be the done IDs sequence. Now all we need to do is reset the to-dos atom with updated to-dos. Please verify for yourself in the browser that clicking the Clear Completed button works as before. We can now delete the commented out version of Clear Completed. Next, we will rewrite the complete all toggle utility function. To start, comment out our current version. We will start a new version of complete all toggle, but this time without specifying a Boolean parameter b. We will derive a Boolean value b directly by inspecting our to-dos map, calculating if not every to-do item is done. Not every ? Is a useful standard library function. Next, we will bind a function that we will name g. It will take a map and an ID. Run assoc_in on the map, taking the path of ID and done, replacing its value with the Boolean b, returning the result as a new map. Next, bind all the keys of the dereferenced to-do atom to the name IDs. Now, our updated to-dos will be generated by calling reduce. Passing in the toArity function g, followed by the initial value of the accumulator, which is the to-dos map, and finally the IDs of all the to-do items. Now all that is left to do is reset the to-dos atom with these updated to-dos. We need to update our call to complete all toggle in our task list component. We no longer need to pass an argument. You can verify for yourself in the browser that toggling all items as complete works as before. We can now delete the commented out complete all toggle function, and also the mmap function above it, since it is no longer used. Good, we have successfully rewritten two utility functions to make use of reduce. One could make the argument that they are easier to read and understand than their previous versions. Refactor to single-state atom. Our objectives are: we will explain what a reagent cursor is. We will refactor our code to use a single-state ratum and cursors. As an optional exercise, we will remove the cursors and refactor all our code to directly interact with our single-state ratum. In ClojureScript, it is not uncommon to store all your app state in a single atom. The advantage of having just one state atom is that we can more easily observe how all of our state changes in response to events, without having to look in multiple places and without requiring an understanding of how the various state atoms affect each other. This makes our code clearer and more maintainable. When using Reagent, any component that dereferences a ratum will update whenever any part of the ratum is updated. If we are only using one single state ratum, then every component that relies on the ratum will update whenever the ratum changes, which may cause performance issues. Therefore, Reagent provides cursors, which behave like ratums but operate like pointers into a larger ratum. Updates to a cursor only cause updates to components that dereference the cursor. First, we will refactor our code to make use of a single-state ratum. Then, we will use reagent cursors to parts of our single-state ratum. We will call our single-state ratum db. Its initial value is a map. It has a key of to-dos, whose value is an empty sorted map. And it also has a key of showing, with an initial value of the keyword all. Now that we have a single-state ratum, we can define reagent cursors that point into it. For simplicity, we will call the first cursor to-dos. Let's start by removing the ratum binding the to-dos var. Create a reagent cursor. It takes the ratum it points into as the first argument. And the second argument is the path to the part of the ratum it tracks for changes. Now, let's also create a cursor named showing in the same way. You can verify for yourself in the browser that the app works just as before. Now, as an exercise in using atoms, let's remove the cursors and refactor our code to work directly with a single-state atom. For an app as simple as ours, it will not noticeably reduce performance. By removing the cursors and just using ratums, we will be preparing our code to make it more comparable with the TodoMVC version used in Reframe's documentation, which we will cover in the next section of this course. However, these changes are completely optional. You can jump to the next video if you don't want to remove the cursors. Okay, there are a lot of changes to make. Let's start at the top and work our way down. First, let's remove the cursors. Our first error appears in the todos arrow local store function. We are dereferencing the todos atom, which no longer exists. We need to get the todos value from the dereferenced db atom instead. Next, in our local store arrow to-dos function, we can no longer reset the to-dos atom. We will need to swap on the DB instead, associating the to-dos field with the sorted to-dos. Inside our addWatch function, we can only watch our single DB state. Now, we only want to update the local storage when the to-dos part of our state updates. Please stop the video now and try to refactor the rest of the code yourself. If you get stuck, resume the video. Please give it your best shot before continuing. Okay, let's continue. We will fix set showing. Now add to do. Next, toggle done. Now save to do. Next up, delete to do. Now complete all toggle. Next, clear completed. Now let's make changes to our view components, starting with the task list. Next, our footer controls component. And finally, the to-do app component. Great! Our app now is in a better form to compare it with the reframed TodoMVC version we will cover in the next section. Make production build. Our objectives are: we will show you how to create a production build that you can deploy. We will show you how to run a report on your production build to see how much space each library takes up. First, stop the development server. Now, we will build the app for production with optimized build settings. Run the build script. Wait until the build has been completed. This may take a minute or so. We will jump ahead in this video. Now that our build is finished, we will print a detailed build report. To do so, we will run the report script as follows. This will also take a while, so we will jump ahead again in this video. Scroll up to the top of the report. We can see here that the pprint library, when optimized, uses up about 92 kilobytes of space. There is no need for us to include the pprint library in our production build. Let's go back to our code and remove it. We will first comment out pprint from the require form. Now we can discard printing to console in the addWatch function. We should also ignore the key argument in the watch function. Now let's go back to our terminal. We will build again. We will jump ahead. And we will run the report again. Jumping ahead again to when the report is finished. Scroll up again to verify that pprint no longer is in our production build. Now open up the project view in your code editor. We can see the public folder. All you now need to do is deploy this public folder to your web server and you're done. I have deployed it to Netlify at this URL. That's the end of this section. Congratulations on making it this far.